Well, welcome back, guys. We are going to start our volume sections today. So this is section 7.2. This is going to be volume of solids with known cross sections. And hopefully you have four models around the room. They look like I have a picture of them on the screen here. What I'd like for you to do is pause the video and jot down some ideas, talk with someone around you about how each of these sections were formed. What are similarities? What are differences? And then I want to kind of formalize your ideas there. So go ahead and pause the video, take 3 minutes, jot down some ideas. All right. So let's take a look at one of these in particular. Let's take a look at what I think is kind of the tornado looking one, that greenish one with semicircles. If I wanted to construct this perfectly, how many semicircular cross sections would I have? I'd have an infinite number of them, right? And basically I want to sum up an infinite number of semicircular cross sections. So would you kind of agree with this notation? I would want to take an infinite sum, which would be an integral. And can you see what x values I'm going from what to what? We're going from 0 to 1. And I want to sum up a bunch of semicircles. Each one has a teeny tiny width, right? Like the width of that paper. Again, if it were a perfect shape, it'd have an infinitesimally thin width, dx, right? So this would be kind of one way to talk about this shape. So I have this function y equals x squared, and I want to go from 0 to 1, and I'm going to just tack on a whole bunch of semicircles on here, right, until I get to 1. And what I'm doing is I'm setting which piece of the semicircle on the board there. I'm setting the diameter, right? So if I want to figure out the actual volume of this shape, I'm going to need to know the equation of the area of a semicircle based on its diameter, and that's what we're going to get to in just a bit here. But what I want to do first is I'd like to show you kind of how these problems look like. They come with a whole lot of words. But all you really have to do is focus in on the important information, and then they become pretty simple to set up. Typically, you're going to be asked to set these up only, or have a calculator to help you with the computations. Right? Typically, not always, but usually. Okay, so what I'd like to do is take a look at each of those four models, and let's take a look at this first description. So again, a lot of words. Let's read it. It says the region bounded by the graph of y equals x squared, the positive x-axis, and x equals 0.7 is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. What is the volume of the solid? So this is what the problem is going to look like. Right now, I just want you to match the problem to which of these models. Is it, I'm going to go back here, maybe the maroon one, the yellow one, the green one, or the blue one? It's the maroon one, right? How do you know? Well, simply because of this word here. Each cross-section perpendicular to the x-axis is a square. And that was the only one that had square cross-sections, right? All right, let's take a look at this one. The region bounded by the graph still of y equals x squared, the positive x-axis, and this time x equals 1 is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a rectangle. What is the volume of the solid? So which one is this? This is the one with the blue paper, right? How do we know? because each cross-section is a rectangle. Okay, moving on. For this solid, each cross-section perpendicular to the x-axis is a semicircle. So this one is the tornado-looking one, right? That's that greenish one. All right. And the last one, for this cross-section, for this solid, each cross-section perpendicular to the x-axis is a right triangle. So this one would be the yellow one, right? Okay. In a bit, I'm going to have you make your own models with a partner. But before we do that, I want to calculate some of these actual volumes. And before we do that, I want to do a teeny bit of geometry review to make sure we know all our necessary area formulas, okay? So would you take a moment, pause the screen, and jot down what is on here in your notes, and then we'll fill these out together. All right, so just jot down what's on the screen, pause it, and we'll come back and write down the formulas. All right, so let's go ahead and see how much we remember here. So semicircle with diameter d, and you can see why I have this if you look at that, again, that tornado-looking model. We stuck the diameter on each base, right? So I need to know the area of a semicircle with diameter d. Well, let's start out with a radius r. A circle with radius r has area pi r squared, right? So a semicircle would have area 1/2 pi r squared, correct? All right, now how is diameter related to radius? Well, radius is half the diameter, right? So I can make the substitution for r as d over 2. So far, so good? All right, and that's really it. I just like to make this a little prettier so it's a little easier to memorize. So if I square this fraction, I would get d squared over 4, right? So my denominator is actually 4 times 2, which is 8. So my coefficient in front of d squared is going to be pi over 8. 8 needs to be in the denominator times d squared. Okay, and this one probably didn't use a whole lot in geometry, if at all. But I do want you to memorize this. It'll just make these a lot faster for you instead of going through this every time. So semicircle with diameter d has area pi over 8 times d squared. All right, let's do the rest of these. Square with side s has area what? Just side square, right? Rectangle with length L and height H has area what? Length times height, right? Okay, isosceles right triangle with leg L. Okay, well, the area of a triangle is 1/2 base times height, correct? But for an isosceles right triangle, these are equal, correct? And let's call it both of those L. So you're going to have 1/2 L times L, base times height. So L times L would be L squared. So 1/2 L squared. All right, and the last one, equilateral triangle with side S. Does anybody know this or remember this from geometry? I'm just going to go ahead and give it to you. And you can look up the proof online if you're interested. But the area of an equilateral triangle with side S is square root of 3 over 4 sides squared. Okay, you need to have each of these memorized. And some are more familiar than others, right? Okay. Okay, so let's go ahead and find the volume of that solid whose cross sections are semicircles. Okay, and if you could look at it, you can think about how much space 1 cubic unit would occupy. And if you can picture a cubic unit on there, maybe you can see that ours would fit inside that cubic unit. So my answer should be less than 1. It should certainly be positive, but less than 1. So between 0 and 1. Okay. So in words, again, if I want to find the area, or I'm sorry, the volume of this solid, I want to sum up a whole bunch of semicircles, right? So an infinite sum, and we're going from x equals 0 to x equals 1 of a whole bunch of semicircles. Each of whose depth is this teeny tiny dx. Okay, so now that I've identified my shape, I'm going to go find my formula, which again you want to memorize. Again, go ahead and pull out all your coefficients in front of the integral. Okay, it'll make it easier to work with. So for a semicircle, my area is pi over 8 times diameter squared, right? So I'm going to pull out that pi over 8 in front of the integral. 0 to 1, and then d squared dx. All right, so now all I have to do is find what the diameter is. We'll take a look at that model. The diameter changes each time, does it not? It is equal to the height of that function, which is going to be f of x, right? So I get pi over 8 times the integral from 0 to 1, and the diameter is f of x. So I want to square f of x dx. Okay. All right, let's go ahead and find what this is equal to. Let's use our calculator. So go ahead and pull up your calculators. Make sure I'm on the pointer here. Okay. I would like for you again to get into the habit of putting your functions in your y equals and then just grabbing them in your home screen. So my function was y equals x squared. Okay. Now let's go to our home screen and type in that integral that we had. Hopefully you wrote it down in your notes. It was pi over 8 times the integral, math 9, from 0 to 1 of f of x squared, right? And we put f of x into y1. So there's a couple ways to find y1 if you have the newer operating system. Alpha f4. So alpha f4, it's right there, number 1. If you have an older operating system, or if you are working with an 83, you can go to vars. By the way, it's a good idea to get in the habit of opening up a new set of parentheses here. But go to vars, yvars, function, and there it is. Okay. And we wanted to square that, right? Diameter squared dx. And there it is. Follows our approximation that this should be less than 1. So always round to how many decimal places? 3 decimal places. In AP, you can either round or truncate, so 0.078 is fine. So 0.078 or 0.079 would have been acceptable too, either one. All right, why don't we try another one? Let's do the one with rectangles. Okay, so let's just talk basic first. I want to sum up a whole bunch of rectangles from 0 to 1, right? And each rectangle, each cross section is going to have this teeny tiny, infinitesimally thin depth of dx. Okay, recall still f of x is what? X squared. Correct. All right, now you're going to need a little bit more information here because I know that the area of a rectangle is what? Base times height, right? And if we are looking at that model, we can see that the base is what's stuck to f of x, right? So the base is f of x. Now you're going to need to be given some more information, so I'm going to give it to you here. I'll also let you know that the height, the height is equal to half the base. If you look at one of those rectangles, that's probably believable. Okay, so for area of a rectangle, I have base times height, or length times width, either way, right? For our case, the base is what? It's f of x, right? And the height is 1/2 the base, so 1/2 f of x. So really, each area is 1/2 times f of x, or f of x squared, right? Okay, all right, so let's come back to our integral. So I want to sum up a whole bunch of rectangles from 0 to 1. And now I know that the area is going to take this form here. So I'm just going to plug that in for my rectangle formula. Again, I like to pull out the coefficient of 1/2. We're going to square f of x, right? Dx. Okay, why don't we plug that into our into here also. Maybe. All right, so if you are lazy like me, you could just pull up our previous integral and just change that fraction to 1/2 instead of pi/8. 0.1. Okay. So slightly larger, right? Okay. All right, in just a moment, again, you're going to get a board to work with, a foam board to work with, some pins and paper that you're going to cut out into your cross sections, and then you're going to be given one of these cross sections, and you're going to be asked to find the volume. All right. So I'm going to have you do that at the end. I thought to finish the lesson we would do the first problem from your homework. Okay, so if you would take a look at the volumes of known cross sections. Let me pull it up here. Okay, so it says part A, sketch and shade each given region. I'm okay with you using a calculator for these. If you can graph by hand, that'd be better. Then part B, it says set up an integral that represents the volume with this, the volume of the solid with the given cross section. And then part C, use your calculator to compute the volume, just like we did in the last two examples. Okay. All right, so it says for number 1, the region bounded by y equals x squared plus 1, y equals x, and x equals -1, and x equals +2 with square cross sections perpendicular to the x-axis. Okay, so part A, let's go ahead and sketch a picture here. Let's see if we can get... Okay, so x squared plus 1 is going to be the standard parabola shifted up 1 unit, right? And then y equals x is just the identity function. So crosses through the first and third quadrants. And then we also have the graphs x equals -1 and +2. So something like this. Okay, and what I want to do is take this region here, make that the base of my solid, and stick a whole bunch of squares on here. So my squares are going to come out of the screen. Okay, picture little squares on here coming out towards you. All right, so I want to sum up a whole bunch of squares. And I want to go from what x value, no, remember perpendicular to the x-axis, right? Whatever it's perpendicular to is going to tell you if you use x values or y values. So in this case, perpendicular to the x-axis, so I need to know my x's here. And looks like we're going from x equals -1 to x equals +2, right? Those were given. And my shape is a square, and the area of the square is side squared, right? And each square is going to have an infinitesimally thin depth dx. Okay, so now I just have to figure out the formula for each side. Well, each side is going to be a top minus bottom, isn't it? So top is going to be the parabola, bottom is going to be the line. So each side is going to be top x squared plus 1 minus bottom x dx. Okay, all right, so let's go ahead and put those in our calculators. Oops, and I did forget a squared here, didn't I? All right. Why don't we go ahead and practice, even though these aren't super long functions. Let's go ahead and practice by putting our functions in here. So my first function was x squared plus 1. My second function was y equals x. And then I wanted to take the integral from -1 to 2. Open up a new set of parentheses here. And we wanted to do top minus bottom. And I don't know if you can see here, but the top one again was the parabola, which was y1. Minus bottom, which was y2. And that's what each side would be. And then I want to square that, right? Because I'm taking squares. Dx. And I'm getting 8.1. All right. All of these should be positive answers. If they're not, you did something wrong. Okay, you shouldn't be getting negative volume. All right, so my answer is 8.1 cubic units. Alrighty. Okay, there are three problems that are in terms of y. So you take cross sections perpendicular to the y-axis. And I have those graphed here for you. So if you'd like to take a picture or screenshot, they're also on our website in our notes. So if you'd like to access those, that's totally fine. I also have the key on our website. I believe there is one mistake on there, but I think I have that fixed right underneath it. So just read our website there. But the key is there, so please check yourself as you go. Again, by all means, use a calculator once you have the integrals set up, but be sure that you show both the sketch and the integrals before you put it into your calculator. All right, well, that's it. So have some fun with these volumes, and I will see you next time.